1.52 terabits per second? That figure might sound like just another lab statistic, right? But it is actually enough speed to stream 1.5 million YouTube videos in high definition simultaneously. Hello everyone! Today we are going to dive deep into something most people never see, but is the heart of the digital world, the optical fiber backbone of the global internet. While we're all excited about 8K video, generative AI, and the arrival of 6G, did you know our existing infrastructure is running into a terrifying physical dead end? Scientists call it the Nonlinear Shannon Limit, a glass ceiling that restricts data capacity to about 100 terabits per second per core. If we can't break through this wall, the dream of a seamlessly connected world might remain just that, a dream. But the good news is we now have a game-changing innovation called Space Division Multiplexing, or SDM, to save the day. To give our engineers and corporate colleagues a clear picture, global data traffic is currently growing by a staggering 40% every year. Think of conventional single-mode fiber, SMF, as a single-lane road that has served us for 40 years. Now, AI and 6G traffic is flooding in, and this road can no longer handle the load. The smartest solution isn't trying to squeeze the cars or make them drive faster on the same lane. It's adding lanes in the spatial dimension. This is the core of SDM technology, turning a hair-thin strand of glass into a 3D data superhighway. A recent mind-blowing world record achieved 1.02 petabits per second. You heard that right. We've entered the petabit era, and we did it using an industry-standard 125 micron fiber cladding. The first pillar I want to present is multi-core fiber. Instead of one core, we embed multiple light-guiding cores within the same cladding, 4, 7, or even up to 19 cores. That 1.02 Pbps world record was achieved using a 19-core coupled core fiber over a distance of 1,808 kilometers. This proves that this technology isn't just for the lab. It's ready to connect major cities and even span continents. The engineering challenge here is intercore crosstalk, but we solve this using advanced MIMO, or multiple input, multiple output digital signal processing. It's essentially taking the complex mathematics used in wireless systems and applying them to light. Beyond increasing core counts, we are also developing few-mode fiber. FMF is like allowing cars to stack vertically in a single lane without colliding. We use different light patterns, or modes, such as orbital angular momentum, or OAM, to separate data channels. Recent data center experiments have shown we can transmit 1.6 terabits per wavelength without needing complex MIMO processing over short distances, which is incredibly energy efficient. This is the start of the energy-efficient scaling that modern organizations truly need. Another technology I'm incredibly excited about is hollow core fiber. For a moment, forget about solid glass fibers. Hollow core has a hole in the center that allows light to travel through air rather than silica glass. The result? Light travels 47% faster, and it reduces latency by more than 30%. For industries where a single microsecond is worth a fortune, like high-frequency trading or massive AI computing clusters, hollow core is a godsend. Tech giants like Microsoft are already testing this because it minimizes nonlinearity, allowing us to send light at higher power without distortion. And if you think we're only expanding in the spatial dimension, think again. We're also expanding in the dimension of color or frequency with multiband YDM. Traditionally, we only used the C and L bands, but researchers just set a new record of 402 terabits per second by unlocking all 6 bands, O, E, S, C, L, and U simultaneously for the first time. This requires new types of amplifiers like bismuth-doped fiber amplifiers and Raman amplification working together to cover a massive bandwidth of 37.6 terahertz. This is the most efficient use of a single glass resource humans have ever achieved. As corporate professionals and engineers, we must also consider cost and commercial viability. Replacing the world's single-mode fiber with multi-core would be astronomically expensive. Therefore, a clever strategy is using spatial bypass and joint switching.
Instead of switching every single wavelength individually, which requires expensive equipment, we switch them as a group called a spatial superchannel using spatial cross-connects, or SCXs. This drastically reduces the number of switches needed, cuts energy consumption by over 60%, and significantly lowers the cost per bit. So what will be the brain managing this petabit-level complexity? The answer is AI orchestration. Today, we use deep learning and neural networks like LSTM to perform real-time equalization or signal balancing. AI predicts signal interference and tunes the system automatically, making next-generation networks zero-touch environments. This is a crucial learning area for 6G-era engineers. AI is no longer just a data consumer. It is now the traffic controller of the fiber network. The conclusion is clear. The future of communication isn't just about being faster, it's about being smarter and more efficient in both space and energy. SDM, hollow core, and multiband technologies will be the pillars that make 6G a reality and support an AI world that is infinitely hungry for data. Investing in this infrastructure might seem far off, but it will drive massive economic value and level up digital access for everyone very soon. Get ready, because the optical superhighway of the future is being built today.